Hello, welcome to session number 17 in the series Microwave and Millimeter Wave Circuit Design. My name is Anurag Nigam, and in this session I'm going to start with the communication systems and radar systems, and I'm going to start with the communication system first. So what I'm going to do is I'm going to present to you some basic uh, on a communication system, right? And then from there I will go from a system level to a component level, right? So the first thing, what I'm going to look into is what is called radio front end. So what happens is, let's say if you're going to transmit a signal, right, through a wireless medium or even a wired medium, right? So what are you doing? You are basically taking a signal which is a digital signal or an analog signal, and then you are modulating a carrier frequency with that, and that carrier frequency is going to be much higher than the signal which carries the information, right? And then you transmit that carrier modulated signal, right? And then you receive it on the receiver side. This way you are going to transmit information from transmitter to receiver, right? So the most important part is the carrier frequency you are going to transmit, and the signal is basically modulating that carrier frequency, right? So what's going to happen is that uh, the signal is going to degrade as it goes through the medium. It's going to degrade, and it's going to degrade for many reasons. One is the basic nature of an antenna, right? So let's assume that the antenna is a isotropic in nature. An isotropic in nature antenna means that its radiation pattern is like a ball, right? A uniform sphere, right? So let's see what it looks like. So let's say if I was to consider a sphere, okay, so this would be a sphere, right? So if you shade it right, it would look like a sphere. Okay, does it look like a sphere? Yeah, so kind of like sphere, right? So this radiation pattern is like a sphere. Now, uh, the total surface area of this sphere depends on the radius. Am I right? So it is 4 pi r square, right? So let's say if I have a power, right? So that power is, okay. So the power I'm radiating, so I don't want to write equation over here. So the power I'm radiating is, let's say, PT, right? Okay. So now this power, let's say, is coming from a point source, from a point source, right? So it is going to be uniform in all the directions, right? So if it is uniform in all the direction, then the pattern is like a sphere. Now if I go a distance r from that point source, right? So then the power density would be PT divided by, so this power density would be PT. So let's put that there. Okay, PT divided by 4 pi r square, right? 4 pi r square. Okay, so basically the power density is varying with r square from a point source. Now if I was collecting that power on that sphere, right, with the aperture A, then the total power I would have received will be PT divided by 4 pi r square into A. That would be the power I would receive at any point on this sphere, right? If I collect it with the area A, right? Now that means that the power which is received, so this is going to be the power received, right? So this power received is going to drop with r square. So power received is going to drop with r square, right? So now what does this mean? It means that as you go away from the point source, the power is dropping by r square, right? So this is referred to as path loss. Insert So this is referred to as path loss. Right. Now if I was to give a certain gain to this antenna such that the pattern is no longer a sphere, but it is something different from a sphere. So for example, let us consider that uh, that the point source is radiating something which is a beam, right? So let's draw a beam. Okay, so from the source you have a beam which is kind of doing, sorry, let me bring it to the center and then draw it. Okay, so from a source, uh, insert shape, insert shape. Okay, so from this point source, instead of going sphere, I take the power and project it in a certain direction, right? Right, so I am going to radiate the power in a certain direction instead of irradiating it uniformly. Okay, so let's say this is the uniform radiation, right? So it is radiating in this form, right? So let us give it just 1 second so that I don't mess it up. Okay, so let's say the power is being radiated. Let's give it a different color. Okay, this power is radiated from the same source, but it is in this format. Okay, so let me add a transparency to it. Okay, so it is the same amount of power. It's the same amount of power PT, but I'm radiating in this form, right? And if I was to take a cross section of this, right? So if I was to take a cross section of it, right, then it would look like this. Insert shape. Uh, so let's draw axis, right? So let's cut this wave pattern, right? Let's cut this antenna pattern. So the one of the antenna which is isotropic, it is going to radiate. Uh, it is going to radiate like this, correct? Okay, so it is radiating equally in all the directions. Okay, while this one, okay, is not doing that. Sorry, this one is radiating this way, correct? So now it is the same amount of power, but then I'm seeing a certain antenna gain, right? And that antenna gain is AT, right? So I am going to have the power which is going to be collected will be isotropic, will be PT by 4 pi r square, right? But then if I give antenna a certain directional gain, then the power received would be higher than that, which will be multiplied by the transmit antenna gain. And this is an aperture. This is not the antenna gain. This is an aperture. So let's just make sure that this is an aperture. AP. Receiving antenna aperture. This is the area. This is not the gain, right? Okay, so now what is going to happen is the power which was dropping by r square will not be dropping by r square. It will be dropping by a smaller factor. If I absorb this gain AT in this fraction 4 pi r square, then it will not be dropping as r square. It will be dropping at a much lower rate, which is r raised to n less than 2, right? So the power will be dropping much less. So then the path loss is going to be less, right? So that's depends on the directional antenna, right? If you have an isotropic antenna, then the power is going to drop as 4 pi r square, right? Now, so that is the loss which you cannot get rid of. Only thing that you can do is you can make the antenna to be directional, both transmitting and receiving antennas to be directional. That's how you can minimize the path loss. Okay, so now let's go back to what are what happens to the signal when you send it through, right? So just bear with me. What happens to the signal when you send it through, right? I was discussing over here. Yeah, so you transmit a signal, it goes through a path loss. Then other deterioration to the signal can be the attenuation in the medium, right? Now this attenuation is frequency dependent, right? So what's going to happen? Uh, for example, let's say we are in K band, 18 to 22 gigahertz. This is a water absorption band, right? So there is water vapor in the clouds, right? This is in the atmosphere. So when it's humid, the water content is more. Then the attenuation of the signal in this band, 18 to 22 gigahertz, is going to be more. So that is the problem with the K band, right? And if you have Q band, right, which will be K under, that's why it is called Q, right? So if you look at the frequency band, 12 to 18 gigahertz, that will be called Q band, Q band. So Q band sees the same kind of absorption but not as severe as in K band. And then Ka band, which is above K band, Ka, right? So that goes from 22 to, let's say, 26 gigahertz, right? In that band also you are going to see water absorption but not as strong as in K band, right? So this is the attenuation due to absorption. Again, if you go to 60 gigahertz band, right, 60 to 66 gigahertz, you are going to see oxygen absorption band, right? So this is a attenuation due to absorption. So one is due to path loss, other is due to absorption. And the third one is, let's say if you transmit a signal from a transmitter to a receiver and it bounces off various objects in between and reaches the receiver in different phases, and at some places it is going to add up and some cases it's going to subtract. Now what happens in this case is that you are going to see some places you are going to see fading, or some frequencies you're going to see fading of the signal, right? And so there is a loss because of fading, right? So these are the various losses to the signal, okay? And when we are receiving it on the receiver, it is not just the signal which I'm concerned about, but signal related to the noise, right? So when you are talking in terms of receiving a signal, you are not only talking in terms of signal strength which is being received, but how much stronger is the signal above the noise. So the noise is another factor which is going to affect the signal received, right? So what is the role of the PA? The role of the PA, right, is to amplify the signal, okay, or raise its power level to a level so that it can overcome the path loss for a given distance, it can overloss the attenuation, and it can also give you some margin on fading, right? And this is also in considering that the noise is also going to be picked up by the signal, right? So the signal has to be stronger than the noise by a certain level, right? So this thing has to be overcome by the PA. So PA basically is going to boost the power before launching it into a medium. Medium can be a wireless medium or a wired medium. Now, so one of the specifications of a PA would be the power output, and that really depends on the distance between transmitter and receiver, and also the what is the minimum signal to noise ratio which is expected at the antenna by the receiver, right? So that would decide how much power should be put out from a PA, right? So now in a communication system, we have got what you call radio front end, and radio front end comprises of a PA which boosts the power, and LNA which basically once it receives the signal it is going to amplify the signal without adding any of its noise, right? So it's called a low noise amplifier. So low noise amplifier and a power amplifier, they are the key components of a radio front end. They basically are involved in scaling the powers, right? And another thing is that the antenna is a radiating element. Both transmitting antenna and the receiving antenna is a reciprocal of that. It's a receiving element, right? So between antenna and the power and the PA and LNA, there is another thing which may be what you call a circulator or a switch. Now, why is that there? Because if we have a common antenna to transmit and receive, so let's say there is one terminal which transmits and receives, the other terminal also has a transmitter and receiver, right? So we need some mechanism to share the same antenna for transmitting and receiving. Now, in case transmit and receive take place at the same time, that is in the same time slot, then what's going to happen? There is going to be a frequency selective network which will isolate the two paths. So basically you will be transmitting in one frequency and receiving in one frequency, and this antenna sharing is done using a circulator, right? Now, in case of a TDD system or a time division duplex system, okay, the transmit is going to take place in a certain time slot, and receive is going to take place in a different time slot, though they may occur at same frequencies, right? So in that case, there would be a switch in this switch in between, which will be also called a diplexer or a TR switch, right? So on both sides, on both transmit and receive chain, there would be a circulator or a switch which will be sharing the antenna, and in addition to that, there would be a band pass filter. Now what happens is, whenever you do frequency conversions, right, then the spectrums fold over each other, right, and this may result in more noise than what you are expecting, right? So in that case, you might have to have to filter out the signal in a certain frequency band, so you are going to receive in certain frequency band. This reduces the noise and then improves the signal to noise ratio. That's why you are going to see a band pass filter both on the transmit and receive side, right? So this basically comprises what is known as the radio front end. So in this session and the subsequent sessions, I'm going to design this radio front end, and I'm going to use one typical process which is not a very modern process, because the gate lengths are 0.5 micron or 0.5 micrometer, right? So this is a gallium arsenide and the device is a PHEMT, right? So I'm going to use that just to demonstrate what is a low noise amplifier and what is a power amplifier, and also design probably a TR switch, right? So role of a power amplifier is very clear, so let's write it down. Okay, so this is explaining path loss. Okay, so insert text. Okay, role of a power amplifier fire. Okay, A is to boost signal to so boost signal to overcome, okay, overcome signal losses in the medium. Correct? Okay. Now, what are the various signal losses? One is the path loss, and basically you control it using your directional gain of antenna or antenna subsystem. Then you are going to deal with attenuation. Okay, this is because of absorption in various bands. For example, vapor absorption band, or let's say oxygen absorption band or nitrogen absorption band, right? So the next thing is you are going to see fading. Okay, and this fading is due to multipath, right? Fading is due to multipath, right? And the last one is the noise pickup. Noise pickup. So the power has to be boosted so as to overcome all this. So this is the role of a power amplifier. Now, uh, so so that's the role of power amplifier. Now let's see. Okay, uh, what are the characteristics of a power amplifier, right? So one of the characteristics of a power amplifier is the power level, right? So characteristics of power amplifier. Okay, so in the characteristics of a power amplifier, we have got output power. And what does the output power depend on? The output power depends on uh, basically desired signal to noise ratio at the receiver, or receiver sensitivity to be specific. I would say it depends on receiver sensitivity and maximum distance, right? These are the two factors, right? Let me move it to the side. Okay. uh, Next is, so if it has to boost the power, right, so this must be the most power consuming component in a transmitter, right? So in that case, the second important characteristics of a power amplifier is efficiency. Okay, now let's represent a power amplifier by a symbol, right? Okay, so the most common symbol used is this. Correct. So this is a symbol of the power amplifier. Okay, so now if I have a certain output power and if I have a certain input power, so I would have P out and P in. So I'm talking of P out, sorry. So I'm talking of P out, right? And then I am talking about P in. Okay, now if I consider P out divided by P in, that would be called the gain, right? So that will be called the gain, P out by P in. Now this is the simplest definition of gain, is P out by P in, but this is specifically called what you call a power gain, right? So we will come to other forms of gain also. So this would be P out by P in. So this will be P out divided by P in, right? So that would be called the gain. So the next important characteristics is the gain. Okay, now whenever there is a gain involved, right, what might happen is I might put in P in power, but a portion of that power goes through as P in dash, right? So what I can do is insert. Okay, so I am looking at P in dash. In dash. So this is the power which is available to the PA. Okay, this is the power which is available to the PA for amplification. So I am putting in P in, but there is a certain network here, okay, which is matching it. So basically we are in a, let's say in a 50 ohm system, right? So there is a matching network here, right? Insert. Okay, so there is a matching network. So I'll say matching network. So just bear with me. Okay, so there is a matching network here, right? So this matching network, the role of the matching network is it will take input. So you are going to match the impedance, right? Now in case the impedance is not perfectly matched, right? It's not perfectly matched to 50 ohm, right? So what is going to happen? What's going to happen? A part of the power is going to be reflected back, right? So I will put here a part of power which is reflected back as PR. Sorry. Okay, a part of power is reflected back. Okay, so now what's going to happen? If I was, so same thing can happen on the output side too, right? So basically the PA is putting out a certain power, but then all the power is not going to the load. Okay, but what power goes out is P out. Okay, but the available power at the output is P out dash, right? So let's say the available power at the output is P out dash. Okay, but what has gone through is P out only, right? So what is reflected back is PR, POR. I can say POR. So a POR is reflected back. Okay. So now, if I was to take a ratio, PR by Pin, right? So that would be basically the reflection coefficients, right? PR by Pin will be reflection coefficient. It will also be expressed in dB. It will be called return loss. So basically we have return loss at the input and return loss at the output, right? So P out by Pin is the power gain, right? But then there can be other forms of gain also, right? I might be matched conjugately at the input. So Pin is equal to Pin dash. But at the output, I may be mismatched, right? So I can say I have a power gain. Okay, so I have a power gain which is P out by Pin. But then I might be matched to put out power on the input side. So Pin is equal to Pin dash, right? And P out is not equal to P out dash. So we have a power reflected back into the PA. In that case, P out divided by Pin dash. Okay. So now this thing can be written as Pin dash. And I'll tell you why it is only on the input that I'm considering. Why not on the output later on? When we go through the design, you will know. Okay. So this would be called the what you call transducer gain. Right. So this will be called transducer gain. Next is if I was to consider, so basically power gain absorbs both the mismatches and input and output. Transducer gain absorbs the mismatch only at the output, right? And then you have got available gain. Okay, in that case it will be P out dash divided by P in dash. This is basically also the maximum gain, right? So sorry, so I can say this is P out dash. Okay, so this would be called available gain, or it is also called the maximum gain. This usually happens when input and outputs are conjugately matched, right? So this will be called G max or maximum gain. Right. Now, in this case, we have also PR by Pin. That will be called the return loss, right? So if I do PR by Pin, it will be a negative number because PR is smaller than Pin. So this number is less than 1. So its log in dB would be a negative number, right? So PR by Pin, right? That would be called the return loss. Similarly, I can consider it the P out P PR by P out dash. That would be called the 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 output return loss, right? So now the next parameter is the return loss, correct? Okay. Uh, Besides this, what else is important for a PA, right? So you have got output power, efficiency, gain, return loss. Okay. Then there are other parameters which become important later on. Okay, so this is basically what. Okay, so there are two things. One is VSWR. So you remember in Smith chart we talked about voltage standing wave ratio, which is basically 1 plus mod of gamma divided by 1 minus mod of gamma, right? So in the previous session, if you refer, you'll come across VSWR, voltage standing wave ratio. Now there are two voltage standing wave ratios which are important. One is the VSWR safe operating. Safe. Okay. The other one would be called performance. So what it means is that if I have a mismatch on the antenna or the PA sees a mismatch, then what mismatch is the maximum mismatch uh, which is tolerable, like it still performs even if despite of a mismatch. That will be VSWR performance. It can be 2:1, 2.5:1, or whatever. Then there is something called safe operating VSWR, in the sense that if I show a mismatch to the output of a PA, then POR is going to be reflecting back into the PA, and this may basically blow up the PA. Okay, so if I show it like 10:1 or a 20:1 mismatch or VSWR, right? Is it going to survive? The PA going to survive? So this is another very important. This is also referred to as ruggedness. Okay, so let me just move it to the side. Okay, so this is also referred to as ruggedness of the PA. Okay, so this is another. The third one is the quiescent current. So basically, when there is no signal into a PA, what is the current drawn by the drain? That is called the quiescent current, right? So these are the important characteristics of a PA, right? Now we will discuss, one more thing I want to discuss here. Let me see the time here. Okay, half an hour. One more thing I want to discuss here is what you call. Okay. Okay, let me talk about efficiency. Okay, so efficiency basically can be expressed as, so if I was to say efficiency, so let me put here, efficiency again can be mentioned in three ways. Okay, one is called the drain efficiency. So usually efficiency is represented by a symbol which is neta, right? Where is that neta? Alpha, beta, gamma, T, everything is there, but neta is not there. There it is. Okay, so this I can say is drain efficiency, or also called the collector efficiency. This would be basically uh, P out. So this is RF power, right? P out divided by PDC, which is the DC power input. Okay, PDC. Okay, so this will be called what you call the drain efficiency. Okay. Okay. The next thing is known as power added efficiency. Okay, so this will be PAE. Sorry. How much power, RF power, has been added? Okay, so the net RF power added is RF power output minus the RF power input. Okay, so okay, RF power input. So this will be called power added efficiency. And yet another efficiency is called conversion efficiency. So the output is RF, but the input is RF plus DC. So how much of the input is converted to output, right? So this will be called conversion efficiency. Okay, so this will be P out divided by P in plus PDC. right? So this will be called conversion efficiency. Sorry. Correct. So efficiency is also mentioned three ways. Okay, and usually we are in a PA, we are be dealing with power gain and power added efficiency, right? So these are important, and when the gain becomes large, then these three efficiencies they come closer. So when the gain becomes very large, then these three efficiencies will be closer, right? So this is about efficiency. Return loss, I'm going to show you another slide on return loss, right? So let's go ahead and show you that. So this is about the power gain, and let's look at return loss. Okay, here. Okay, so now if you remember, I defined S parameters, right? S parameters are scattering parameters, or they are reflection and transmission coefficients under a special condition. Under the special condition is that the ports other than those under investigation are terminated into characteristic impedance of the system. That is, they are not the source of power into the network. Whatever is thrown at them, they are going to absorb it. So nothing comes back. So only those ports which are under investigation, right? They 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 can be mismatched, but all other ports have to be matched. So that is the definition of S parameters. So in a two-port network, we had S11, S22, S21, and S12. Now, is S11 the return loss or S22 the return loss? Answer is no. It is a return loss under a special condition, right? And again, similarly, S21. Is S21 a gain? No. It is a gain under a special condition, right? That the both the ports are matched to 50 ohm, right? Similarly, reverse gain is also S12 only when both the ports are matched to 50 ohm. In all other conditions, it will not be called the gain or the reverse gain. Now, here I am showing you if I put power into the PA, then I am seeing a portion of power being reflected back. So that ratio of reflected power to the incident power is called gamma in. So this will be gamma in. Now similarly at the output, if I put out a power P out and POR is reflected back, so POR divided by P out will be called gamma L, or the load reflection coefficient, right? Now if I put the power back into the source from the amplifier, right? So a part of it is reflected back again into the PA, right? So that ratio to the power which is incident onto the source is called gamma S, and similarly we'll have a gamma out, right? So you can see the directions of these arrows, right? And then the ratios. Now a special case is when gamma L equal to gamma S equal to gamma in equal to gamma out equal to 0. That means that both the ports are conjugately matched. In that case, S21 would be the forward gain and S12 would be the reverse gain. Same is true in case of return loss, right? If gamma L equal to 0, right, then what's going to happen? Then this gamma in is equal to S11 square, right? And similarly, if gamma S equal to 0, then gamma out is equal to S22, right? Hmm. I did a mistake here, right? This is gamma L load. So this should be gamma S. Gamma S. So I did a mistake here. I have written it kind of opposite. But then this should be S22. So let me correct this. S22, and this will be gamma out. Okay, and this will be out, and this out, and this is out. So this is gamma out, and then gamma in. Sorry, so sometimes I do mistakes. Gamma in is this voltage ratio square. Gamma in and in, and this will be S11, and this will be gamma S. Now it is correct. Okay, so now you can understand gamma out is equal to S22 when gamma L equal to 0. Gamma in is equal to S11 when gamma S equal to 0, right? So this is a return loss under a special case, right? Okay, so this we understood as a return loss. What is return loss, right? You can express this as 20 log of gamma in as a return loss, and 20 log of gamma out is the output return loss, right? And they will be S11 and S22 if the amplifier was conjugately matched on both sides. Okay, so this is understood. This is out of the way. Okay, so let's look at some other characteristics. This we have seen. Okay, so we will go to other characteristics later on, but let's add here one more characteristics which is called linearity. And this is a very important characteristics when you talk about data rates and all that. So we will discuss this linearity in great detail, as we go. So for now, I am not going to discuss this linearity in this session, right? Okay. So other than that, there are other specifications like stability. Okay. Okay. Now, what is a stability? It's like it can be expressed in terms of power. So, for example, let's say if I put in a certain power and I have a reflection more than what I put in, then this must be the source of that power, right? That's why the power put out is more than the power put in, right? So that means that this PA is oscillating, right? So stability means that it's a property that the device is not oscillating, right? So that's called stability, right? So we will discuss different forms of stability and how to do the stabilization of a device as we go and design it, right? Other than that, let's look at other specs. Other specs are uh, quiescent current we have okay, ruggedness we have seen. Next is mean time to failure, time between failure and yield, right? This is to do more with the production, right? So you design a PA, you do not design a PA as just one component because you are going to do millions of pieces, right? So when you do millions of pieces, how many of them meet all the specs? That will be called yield. And for that, there are different tools available in ADS or any other software to do the yield analysis. What is called Monte Carlo analysis, where you vary all the parameters and then you find out how many parts have basically gone through meeting all the specs to how many parts were tested. So that would be called the yield, right? So that's there. Besides that, there are certain design constraints. Like for example, I might design for a certain size, right? I might design for a certain temperature range, and usually the commercial temperature range is -42 plus 85 ambient, right? And for military it will be minus 85 to plus 85 or something, depends on the defense requirement. Then the supply voltage range also. So for example, let's say I am designing a handheld device which is battery operated. So when the battery is fully charged, it's 4.5 volts. When the battery is fully drained, it is, let's say, 3 volts. Now the circuit has to operate over this entire supply range. It has to meet all the specs. So that's a constraint, right? And the last constraint is the component count, right? So if you have a PA which has everything on the chip, okay, and then all it requires is coupling caps and bypass caps, so that number of components, additional components required is less, right? So component count becomes important because it is really the cost to the customer, right? So these are the specifications of a PA, right? Now there are different types of PAs, right? So now PA basically can be in two systems, right? I have already discussed this. It can be a FDD system, frequency division duplex, in which there is in case there is a circulator. Then there is a TDD system in which there is a switch, right? Now you might be turning off the PA also when the receiver is receiving, and the switch is basically, the switch has moved to a receiver like this. Then your PA is basically supposed to be switched off so that LNA basically doesn't receive any noise from the PA side, right? Because they are in the same frequency band, right? So in that case, the PA has to be switched off. So now what happens is uh, thermal becomes important, right? So why thermal is important now? Because a PA basically takes certain time to settle down, reach a certain junction temperature, and its gain is going to droop. So when the gain droops and you put out any linear modulated signal, then it is going to distort. So basically it has to wait for a certain period of time before the PA stabilizes thermally, right? So this is usually done when there is a preamble in a packet which is being sent. So during that short or a long preamble, the PA is supposed to settle down. That is, it doesn't have a gain droop anymore, right? So that becomes, so thermals become important when there is a TDD system. Next thing which is important is when the switches are usually absorptive type, which means that even if I have moved the switch towards LNA, the PA is terminated still into 50 ohm, right? Or if I have moved the switch to the PA, the LNA is still terminated at 50 ohm, right? So these are called absorptive type of switches. But still, when there is a switching transient in between, there is a period where the PA is totally mismatched, right? So in that case, the all the power is going to reflect back into the PA before it is switched off, right? So so that can blow up the PA, right? So in that case, ruggedness of a PA becomes important in a TDD system, right? Not in a FDD system. In a FDD system, it is continuously on, right? PA is transmitting and LNA is receiving through a circulator, right? Antenna is shared, and it is always on, right? So in a FDD system, okay, the ruggedness is not much of a issue. Second thing is that the circulator, so circulator, what it does is if antenna sees a mismatch, then the circulator basically exposes only a small portion of this Smith chart as a mismatch to the PA. So PA basically ruggedness requirements of a PA in a FDD system is less than compared to a TDD system. Now what are the examples? So the example of TDD system are the computer networks, Wi-Fi, right? And the example of a FDD system is your phone, right? It may be so it is CDMA, for example. Okay, this is an example of your uh, FDD system, right? So you transmit in a different band, receive in a different band here. So that is there. So there is a difference between a PA operating in a TDD system and a PA operating in FDD system. So when you are a designer, you are supposed to know this. Okay, so we have talked about the role of amplifier, we have talked about gain. We haven't talked about linearity because this is a special subject on its own. We will do it. Classes of amplifiers, right? Now, the amplifier, we will come into detail when we design these, right? So I'm not going to push you into designing, every type right away. Okay, so we will go step by step. So now here I can say the amplifier can be linear or switching. Okay, linear means non-switching amplifier or a switching amplifier, and then it can be a mixed mode amplifier, right? So switching amplifiers, the device acts as a switch. So which means that the voltage and current through the device are in quadrature, right? So that will be called a switching amplifier. When there is a voltage across the switch, there is no current through the switch, right? It is off. When there is a current through the switch, there is no voltage across it when it is on. That's the ideal switch. So if you use the switch in that mode, then the amplifier is called a switching amplifier. And then there are different classes of switching amplifier: class D, class E, class F, right? F has got again three type: F1, F2, F3. Class E is a special class which I will discuss and also design in this series, right? And then class D, I'm not going to go into a lot of detail, right? So this is about switching amplifier. In a non-switching amplifier, the device acts as a voltage controlled current source or a current controlled current source, right? So in that case, the device can be class A if the conduction angle is 360 degrees. It can be class B if the conduction angle is 180 degrees. It can be AB when the conduction angle is between 360 and 180, and class C if the conduction angle is less than 180, right? So then there are mixed mode amplifiers, right, where during a portion of the waveform it acts as a switch, and for the other portion of the waveform it acts as a current control or voltage control current source, right? So now how do you compare all these topologies of PA. Okay, there is something called device utilization factor. Okay, and what is this device utilization factor? It is the ratio of what is the optimum power you can get from the topology divided by what is the peak power of the device. That peak power is going to be Vmax across the device and Imax through the device. So Vmax into Imax. Okay, so that is the peak power. And whatever the best output the topology can give to the peak power of the device, that is called device utilization factor. So if you take a class A amplifier or AB amplifier, or let's say class B, okay, push-pull amplifier, the device utilization factor is 12.5%, right? While in class E or class C amplifier, right, a class C amplifier at 120 degrees of conduction, the device utilization factor is 9.8%. Okay, same thing as a class E amplifier, right? The device utilization factor is 9.81%. For a class F amplifier, the device utilization factor is 1.59, I think. Okay, 1.59. And if you use the class F in a push-pull mode like in class D, then it will be twice of 1.59. That will be 3.1 something 8, right? So the device utilization factor for would be the best for a class F amplifier. So basically you can use the smallest device to get the maximum power out of it. While on the other end, class E amplifier has the worst device utilization factor, right? And then all other linear amplifiers, A, B, and C, they are 12.5%, right? Now when it comes to efficiency, okay, class A amplifier has the least efficiency because you are biased at the load line is in the active region and you are biased right at the center of the load line. So basically the entire swing is in this region, right? For example, you see the blue oval here in this curve, right? This is a class A. Now if I start clipping at one of the ends, that will be class AB. And when I clip more than 180 degrees, then it will be class C, right? So that will be class C. Okay, so what happens to the efficiency? The efficiency of a class A amplifier is 25%. Okay, or if it is a transformer coupled, it's going to be 50%. The ideal efficiency of class AB would be between 50% and between 25% and pi by 4%, that is 78%. Okay, at 180 degree conduction, that efficiency is 78.4%. So if you have an efficiency of a class C amplifier as 78.4, class B amplifier is 78.4%, that means it's conducting half the wave. Now if you go class C and you have only 120 degree of conduction, then the efficiency is 89.6%. Now if the conduction angle is 0, then is the efficiency 100%? Answer is no, because then you are not conducting anything, right? So that efficiency with the class C doesn't keep going up as the conduction angle goes down. So that's not the case. A class E amplifier, right, has an efficiency of 100%, or class F also amplifier would have an ideal efficiency of 100%, because the switch, which is the major cause of the loss, has voltage and current in quadrature. So when voltage and current in the quadrature, then there is no loss in the switch, right? That's why the efficiency is going to be ideally 100%. So whether it is a class F or a class E amplifier, the efficiency is 100%, right? Ideal efficiency. So we are going to see all this in later sessions. So other than that, in introductory session, what else do I want to show you? Okay, so I will start constructing these amplifiers. Okay, and then I will show you what is linearity and all that, right? So this is to follow in the subsequent sessions. So keep an eye on this one, right? Because this everything, like, how do you quantify what you call linearity or non-linearity, that I will cover. And then how do you simulate this linearity or non-linearity, and then the modulated systems, what they are, what are different modulation schemes. So that I'm going to cover in the next session. I think this session has been an hour almost, so I'm going to stop here. So this is for the introductory section. This is not the design, but this is important for you to know, right? So after this, I'll jump into designing a gain stage, right, in the next session. Thanks a lot. Thank you.